Hi, everyone. Today we have Fernando as our speaker. He's a PhD student at UCLA and he is visiting LA this summer. Today he's going to talk about his work, Secure Massively Parallel Computing, and let's welcome him.
Okay, thanks for the introduction. Like said, I'm going to be talking about some joint work by Elaine and myself, along with Ilan Komorgodsky and Yanming Liu. And the topic of our work is achieving security for massively parallel computation in the presence of dishonest majority. And this work is based on a paper that we had published in TCC last year. So we're going to be talking about protocols, but we're going to be approaching them from a slightly different angle than we usually do in classical cryptography. And namely, we're going to be talking about protocols where the local space of each machine is much smaller than the total input size. So as like a great example of this, you can think of the Google search algorithm. So if you want to submit, like whenever you submit a query to Google and you hit enter, Google distributes this query to a large cluster of machines, and each of these machines has a tiny piece of the Google index, and all of these machines have to collaborate, essentially run a protocol in order to assemble the output and respond to you. And these types of massively parallel algorithms are everywhere. We all use them like hundreds of times a day. So the question that we're interested in answering is whether or not it's possible to achieve security in this sort of massively parallel context. So we're going to be working in what is called the massively parallel computation model, or the MPC model. And the high-level idea of the model is as follows. So we assume that we have some large input string, and we assume that there's some large number of machines where each machine has local space that's much smaller than the input string, the total input string, and we want to perform some computation over this this input string with our cluster. And so we'll distribute this input string to all the machines, and these machines will run a protocol, and the output for this protocol is defined to be the concatenated output of each machine. So in this model, we generally assume that the local space of each machine is n to the epsilon, where n is the total size of the input and epsilon is some small constant that's less than 1. And like in this talk, since we want to build protocols that are as general as possible, we're going to assume that epsilon is arbitrarily close to 0. And so it follows that the number of machines has to be around the order of n to the 1 minus epsilon. So an important detail of this model is that communication is assumed to cost space. So that means that in a given round, if some machine receives messages from a bunch of other machines, then that machine has to store all of those messages in its local memory in order to process them. And again, if a machine wants, at the end of the run, the machine wants to send some messages, let's say it wants to send a message to several different parties, it has to store a copy of that message for each party it wants to send to. So in particular, what this means is that there's no free broadcast in this model. So we're going to say that a protocol is efficient in this model if it takes much less than logarithmic rounds. So I want to fix some notation before I go on. So for the rest of this talk, whenever I say the acronym MPC, I'm going to mean massively parallel computation. Okay, so the types of questions we're interested in are whether or not it's possible to achieve security in this model. In particular, we want to achieve security guarantees that are similar to those in classical secure computation. So in classical secure computation, the idea is that we assume some of the machines are malicious. We, like, without loss of generality, we just assume that they're all controlled by some malicious adversary. And we want to provide guarantees to the rest of the parties, the honest parties. So the question, so what we try to guarantee is we try to prevent the adversary from learning the inputs and the outputs of these honest parties. And we also try to prevent the adversary from tampering with the outputs of the honest parties beyond what it can do in the protocol. Okay, so the way that we satisfy this kind of like these kind of intuitive security properties is through this very classical game definition, game-based definition. And so I'm going to go through this definition quickly for you. So in this definition, we have two experiments. They're called the real world and the ideal world. So in the real world, the corrupted parties interact with the honest parties in the same way that they would in a normal execution of the protocol. And then the output of the experiment is defined to be the adversary's view jointly with the honest party's outputs. So in the ideal world, the corrupted parties don't have direct access to the honest parties at all. Instead, they interact with a simulator. And the simulator also doesn't have direct access to the honest parties. Instead, it goes to this trusted party. So the trusted party will take everyone's inputs and then distribute the corrupted party's outputs with respect to the protocol, like the protocol functionality, to the simulator. And we say that the output of this experiment is, again, the simulated view of the adversary along with the honest party's outputs. And so intuitively, if an adversary can't tell which world that they're in, then they shouldn't be able to learn anything in the real world that they don't learn in the ideal world. And it's clear that in the ideal world, the adversary shouldn't be able to learn, like the corrupted parties can't learn anything about the honest inputs beyond what the output of the protocol reveals. So we say that a protocol is secure if these two views of the two experiments are indistinguishable. So this definition actually ports to our MPC model pretty easily without much modification. So the natural question is, can we actually satisfy this definition? Can we achieve security in this model? So let me just quickly remind you what our efficiency requirements are. So each party has to have local space that's bounded by n to the epsilon, and the round complexity has to be very small. So the question is, can we achieve security in this model with minimal change in these efficiency properties? So I think it makes sense to ask ourselves whether the large body of classical secure computation literature, whether this can be applied to this new model. So let's start with GMW, for instance, classical GMW protocol. So if you're familiar with this protocol, you know that even in the first, like even at the very beginning of the protocol, we're going to run into problems because the very first round, every party has to send a commitment of its input and randomness to all the other parties, and every party has to store all of these incoming commitments all at once. So what that means is that it's storing information that's proportional to the entire input size. And it turns out that as far as we know, all the other classical work on secure protocols, they have this general pattern. They all have this simultaneous broadcast phase where every party sends out a message to every other party, and every party has to store all of these incoming messages all at once. There's previous work on large-scale computation, actually, but even this previous work has this exact same problem. So the bottom line is that it's unclear how to use any of this previous work in the MPC model. So the previous work, so there's this recent previous work of Chan et al. In ITCS last year, and they initiate the study of secure computation in this massively parallel model. And they show that the answer to this question is yes. So namely, they build a compiler. So they take any insecure MPC protocol pi, and they show that they can transform it into a pi tilde, which is secure. So it achieves malicious security against up to approximately 1/3 corruptions in the common random string model. So where you assume every party has access to some shared randomness. And furthermore, they do this with very good efficiency properties. So they essentially, like if the underlying protocol is in the MPC model, then the new protocol is still going to be in the MPC model. They have very, very minimal space blowup and round complexity blowup. And as far as assumptions, they use the learning with errors assumption, along with like a compact, fully homomorphic encryption scheme, and non-interactive zero knowledge. So the goal of our work is to improve upon this state of the art. In particular, trains honking. Sorry. So we want to improve on this recent state of the art, and in particular, we want to fix two deficiencies in the previous construction. So the first deficiency is that security only works if the adversary chooses its corrupted parties very selectively. So in particular, it has to choose the corrupted parties before seeing the shared randomness that all the parties will use. And it turns out that if this assumption does not hold, if the adversary can choose its parties after seeing the ZRS, there's like an obvious and devastating attack. Security is like completely broken. And the second deficiency is the corruption threshold. It's not clear if this 1/3 corruption threshold is optimal, since there exist many secure protocols in the classical model tolerating all but one corruptions. And interestingly, both of these deficiencies, they seem tightly coupled to the overall approach of the previous work, because they hold even if the adversary is very weak, if it's semi-honest, which means that it's only allowed it cannot deviate from the honest protocol specification. So the question is, are these deficiencies inherent in the model, or is it possible to tolerate m-1 corruptions? And is it possible to get security after, like again, for adversaries who can choose the corrupted parties after seeing the setup? And because of the limitations of the previous work, we think that it's even interesting, like an answer to this question is interesting even in the semi-honest model. So even if the adversary is semi-honest. So with that, I'd like to state our published results. So we have two results. The first result considers a restricted class of protocols, namely protocols where the output size is small enough to fit on the space of one machine. So think of the Google search algorithm. The results, they all appear like on one page for you. So this is an example of a short output protocol. So in this restricted case, we show that the answer to the question is yes. In particular, we give a compiler that tolerates all but one corruptions in the PKI model. And this security is based on hardness of the learning with errors assumption, along with the existence of an FHE scheme. And for the efficiency of our compiler is essentially equivalent to the efficiency of the previous work. So our second result is in the case in the general case of protocols with unrestricted output length. And in this case, we also show that the answer is yes. We also give a compiler that works for these kind of protocols, and for security in this case, we additionally assume that indistinguishability obfuscation exists. And the efficiency properties of our long output protocol, again, are equivalent to previous work. Okay, so for the remainder of the talk, I'm first going to explain the short output protocol. It's quite simple and it's going to be used as a building block in our long output protocol. And so after I explain that, I'm going to give a high level overview of our long output protocol. And then finally, at the end, I'm just going to mention some follow-up work that we've done since our publication, which I'm excited about. Okay, so our short output protocol is going to use like a major tool that we're going to use is fully homomorphic encryption, or FHE. And so I just wanted to explain what this is quickly. So an FHE scheme is like a public key encryption scheme in that it contains a setup algorithm, an encrypt algorithm, and a decrypt algorithm. But then it also contains an evaluate algorithm, which allows you to perform computations over encrypted plaintexts. So let me explain what I mean by that. Let's say we have three parties. Let's say that party one has the public key, and party three has the key pair, so the secret key as well, and party two has nothing. So what FHE allows you to do is party one can encrypt something, and if it sends the ciphertext to party two, then party two can evaluate any circuit with respect to the ciphertext. And then if party three decrypts this evaluated ciphertext with the secret key, then the resulting decryption should be the evaluation of the circuit over the original encrypted plaintext, which party one encrypted. So for our purposes, we're going to use a variant of FHE called threshold FHE, which works as follows. So let's assume that we have M parties. So in threshold FHE, each party has a secret key share. And so decryption will be a little bit different naturally, so it'll work as follows. So let's say that all the parties agree that they want to decrypt some given ciphertext. What they'll do is they'll run what's called the partial decryption algorithm with respect to the ciphertext and their key. And then they'll then they'll publish these partial decryptions, or these decryption shares. So any party that has all of the shares can run a final decryption algorithm and obtain the decrypted plaintext. And in terms of security, what we want is that all parties have to agree on decrypting a ciphertext in order for the plaintext to be revealed. So in particular, if the last party decides, no, I don't want to publish this plaintext, I'm not going to, so this party doesn't release its partial decryption, then the plaintext should be completely hidden. So for our purposes, we're going to require some additional efficiency properties for this primitive. First, we're going to require that the evaluated ciphertext has a size blowup that's independent of the circuit. And second, we're going to require that the partial decryption sizes are independent of the number of parties. Oh, and finally, we're going to assume that the secret key shares are actually an additive secret sharing of some master secret key that can decrypt a ciphertext by itself. So existing schemes satisfy these three requirements. So there's actually a somewhat large body of work in the classical secure computation setting, which uses threshold FHE to build secure protocols. Namely, they use it to build, threshold FHE is particularly useful to build protocols with very low round complexity. So we're going to be basing our short output protocol on ideas which are similar to this. So I'm first going to explain like the general strategy that these works use, and then I'll explain why it doesn't generalize to our model, and then I'll explain how we fix these problems. So I'm going to describe a protocol in terms of the behavior of party one, because the behaviors of all the other parties are essentially symmetric. So party one has the threshold PKI, so it has the public key, and then it has its secret key share. And then in round one, it's going to encrypt a message, its input and randomness for the protocol using the threshold FHE scheme. And then it's going to send this resulting ciphertext to all the other parties. It's going to broadcast this ciphertext. So at the beginning of round 2, after party 1 has received the ciphertexts for all the other parties' inputs and randomnesses, it's going to directly evaluate the protocol's functionality F in terms of these ciphertexts, and it's going to get an encrypted output of the protocol. So then to decrypt this encrypted output, it's going to use its partial decryption algorithm and send the resulting decryption share. It's going to broadcast this to all the other parties. And then at the end of the protocol, after it's received all of the other parties' decryption shares, it will combine all of them using this final decryption algorithm to get the output of the protocol. So the problem with using this like unchanged in our model is the same problem that I was discussing before, namely like in round 1, all the parties are simultaneously broadcasting their ciphertexts, and they all have to store like all of these ciphertexts all at once. And this happens in round 2 as well. All of the parties will broadcast their partial decryptions, and then they have to store all of the partial decryptions at once in order to use the final decryption algorithm. So what this means is that every party in both rounds has to store information that's approximately the size of the entire input. So in terms of our short output protocol, we're going to use a similar strategy. We're going to use threshold FHE, but we're going to modify the evaluation phase. So in particular, instead of beginning with this functionality F directly, we're going to begin with an insecure MPC protocol pi. And so instead of evaluating F directly, we're going to directly evaluate pi, except we're going to evaluate it under FHE. So let me describe this in more detail. So let's imagine that we have an insecure MPC protocol, and let's fix the notation of this protocol in the following way. Let's say that there is, like, for each party and for each round, there's a round circuit which describes the behavior of the party in that round. So this round circuit will take the state of the party up to that point in the computation, and it will take incoming messages in round I, and it will output the updated state and the outgoing messages for round I, which party 1 in this case will send out. So for our secure version, we're going to evaluate this round function under FHE. So party 1 will have a ciphertext that encrypts its state at the beginning of round I, and it will have ciphertexts incoming that encrypt the incoming messages from the other parties for that round. And then it will use the FHE evaluation circuit with the round circuit corresponding to this round and this party. And the result will be the updated encrypted state and the encrypted outgoing messages. So party 1 can just send these messages to all the other parties. So if we assume that the underlying insecure protocol is oblivious, namely that the communication pattern, like which party talks to which party in which round, reveals nothing about the inputs, then this evaluation phase is secure. And it turns out that it's sufficient to assume this kind of oblivious property because the previous work of Chan et al., they show a generic transformation. So they show how to take any MPC protocol and make it oblivious. So now we're at the end of the evaluation phase. And now party 1 just has a ciphertext of its output that it just needs to decrypt. So like I said before, the problem with the previous strategy was that party 1 would have to receive partial decryptions from all the other parties and store all of them at once in order to run the final decryption procedure. So we need to figure out how to get around this. And it turns out that there's a very simple way to do this. And so we just have to make a simple observation about the particular threshold FHE scheme that we're using. So this particular threshold FHE scheme has a final decryption algorithm that works in two parts. And crucially, the first part is simply addition modulo some Q. So if you have a bunch of decryption shares, you just add them up, and then you can perform the final step. So I noticed that the output to the second step of the final decryption algorithm is compact. And so we can use this to prevent any one party from having to store too many partial decryption shares at once. And we can do it in the following way. So let's go back to the protocol and let's assume that party one wants to decrypt this output. The way that party one will do this is it will first distribute this output to all the other parties. And it can do this in tree-like fashion to prevent having to broadcast to every party at once. And then all of the parties can run their partial decryption algorithms. And then they can sum up the results again in a tree-like fashion so that no party has to store all of the ciphertext at one time, or all the partial decryptions at one time. And then once party one has this sum, it can run the final decryption algorithm on this sum, and then it'll obtain the decrypted output. So if we set the fan-in to this tree along with the fan-in of the previous distribution tree to be lambda, then we get the efficiency properties that we need. Okay, so this is the short output compiler. And so now for the next part of the talk, I'm going to be talking about long output. So to start off, let's try to think about why the short output protocol doesn't work in the case of long output. Like, where does it break down? So the first phase is the evaluation phase, and the evaluation phase proceeds as before. There's nothing about the evaluation phase that doesn't work for long output. But the result of the evaluation phase is different because now each party has its own output ciphertext. So instead of there just being one output ciphertext, now there are M of them. And this is going to cause problems in the decryption phase. So let's think about why. So to understand why, let's think about what party one would have to do in order to provide the decryption to all of the other parties. So like before, party one will have to decrypt the ciphertext, or decrypt its own output ciphertext using its partial decryption. But in addition now, it'll have to run the partial decryption on all the other output ciphertexts as well. And so what this means is that it has to obtain all of these ciphertexts, and that means that it has to store all of these ciphertexts, so we're running into the same problem as before. And so in this case, in terms of running partial decryptions for all of the other parties, it's not clear how to avoid either a space blowup or a round blowup. So we need some sort of new approach for the decryption phase. And so I'm going to tell you our approach for this phase. So our main idea is the idea of what we call a restricted key. So what we need is that we need two properties of our decryption phase. We need to be able to decrypt the outputs first of all, but we also need to hide all of the intermediate ciphertexts that were a result of running the evaluation phase. So we can't leak anything about those ciphertexts. So in a sense, it's like a selective decryption problem. So what we want is we want the parties to be able to run a restricted key derivation protocol, a sub-protocol with respect to these output ciphertexts, where at the end we come up with some special key, sk hat, which has the following properties. So sk hat should be able to decrypt any of the output ciphertexts. but it shouldn't decrypt anything else. Like any other ciphertext, it shouldn't reveal any information. So what this means is that indistinguishability should hold for all other ciphertexts other than the output, even for adversaries that have access to this SK hat. So how would we build such a restricted key? What would it look like even? So I'm going to go over like a first attempt at building such a key. And I'll tell you up front that this attempt is not going to work as is, but it's going to illustrate the main ideas behind our actual construction. So in terms of tools, we're going to use an obfuscator. So an obfuscator will take a circuit C and it will output an obfuscated version of this circuit, which has the same input-output behavior as C. So anyone who possesses the output or the obfuscated version of the circuit can run, can get the same functionality. But we're going to assume that the obfuscator hides the implementation details of C. In particular, we're going to assume an idealized obfuscation that hides everything about the original C beyond its input-output behavior. So we're also going, so our second tool is going to be a succinct commitment. So we're going to assume that the parties have some way of coming up with a succinct commitment to all the output ciphertexts in such a way that that each party has an opening. So there should be an opening for each ciphertext that somehow proves that this ciphertext has been committed to with respect to this commitment tau. So if you're familiar with Merkle trees, you can think of this as being a Merkle tree. Okay, so with those tools, I'm going to describe our attempt. So our restricted key is going to be the obfuscation of a particular circuit, which I'm going to describe. So this circuit has it has a commitment to all the output ciphertexts hard-coded, along with the master secret key. The secret key that can decode anything, decrypt anything. And as input, it'll take a ciphertext along with an opening. And if this opening proves that this ciphertext is in this commitment tau, then the circuit will decrypt. And otherwise, it'll output bot. It'll output garbage. So if an adversary has an obfuscation of this restricted key, and we assume that this obfuscation is ideal, then it's pretty clear that the only way that this adversary can get any output from this key that's not bought is if it gives a valid opening of a ciphertext. And so if this ciphertext is not one of the output ciphertexts, then we contradict the binding property of this commitment scheme. In terms of so because of this, the obfuscated restricted key should hide all non-output ciphertexts. So if you're familiar at all with obfuscation, you probably know that there's a huge problem with this construction, namely that this kind of very strong idealized obfuscation doesn't exist. It's too strong. And this was proven by this seminal work on obfuscation of Barak et al. So I won't go into the details of how we fix this problem in our paper, but it turns out that we were able to use the same overall strategy, namely we give out restricted keys that are obfuscated circuits where the circuit has the master secret key and a commitment hard-coded. But we're able to do this using indistinguishability obfuscation instead of this idealized obfuscation. And so the main tool that we use is a special hash function called a somewhere statistically binding hash function, which we use to construct the succinct commitment. Okay, so now we have some sort of restricted key. So in particular, we have some sort of algorithm that takes the master secret key and a commitment to all of the output ciphertexts, and it outputs a restricted key that we know will only decrypt the outputs. But we're not done quite yet because we need some way for the parties to actually obtain this secret key. And so there are some problems with this because no party should know the master secret key. So they can't just evaluate this algorithm directly. Because if any party knows the master secret key, then all security is lost. So essentially what we need is we need a secure MPC protocol, so a secure protocol in the MPC model for evaluating this restricted key derivation algorithm. And this might seem like a catch-22, but notice that the output of this restricted key derivation algorithm is small. And we already have a small output compiler. We have a compiler that takes any insecure MPC protocol as long as the output is small, and it can give us a secure version of that protocol. So there's a very simple insecure protocol for computing the restricted key. If we have all the parties and they have an output ciphertext, then they can collectively compute a succinct commitment, and they can do this in an MPC way. And they can also, of course, sum up their secret key shares using a tree-like fashion as before. And then they can just, and then any one party, let's say party one, can just derive the key, the restricted key directly. So now that we have this insecure version of the protocol, we can just use our short output compiler on this protocol, and then and now we have a secure version. And so with this new subprotocol, we've completed our long output decryption phase. Okay, so I'd like to conclude by summarizing our published results. So we show that any MPC protocol can be made semi-honest secure in the PKI model against all but one corruptions. And this is the first such result in this model in the dishonest majority setting. And in terms of the assumptions we use the hardness of LWE, we use the existence of an FHE scheme, and we use indistinguishability obfuscation. Okay, so before I finish, I'd just like to mention some follow-up work that we've done. So we have two new results. The first result is that in terms of semi-honest security, we are actually able to show that setup is not necessary at all. In particular, we can get rid of the PKI model assumption, and we can just give a compiler that works in the plain model without setup. And the second result is that we are able to get we were able to upgrade our security. So we were able to get a compiler which achieves a malicious security against all but one corruptions, assuming a PKI and succinct non-interactive arguments. Okay, with that, I'd like to conclude. Thank you.
Thanks, Rex. Any questions?
I guess I have a question. Can you remind me how the statistically binding commitment is constructed? Like we use this thing from the previous paper, but actually
how it's constructed.
Is it from LWE?
It's using FHE, I remember that.
Using FHE.
Yeah.
Okay, we can take a look at that paper again. I'm curious. I guess I should have read that paper.
Okay. Yeah, I if you give me a minute, I think I can probably refresh myself and tell you how it works. You remember the property though? The property that it's guaranteeing? It's like you split the input up into blocks, and then you can give a key with regard to some block index. Like the key has a block index embedded in the key, and then for that key, there's only that's statistically binding. So once you have an output of the hash function, you know that that there's only one
I see.
like that that perfectly binds to that that particular
Yeah,
block.
so some index
with-
is like perfectly binding.
Yeah, and you
everything
can't.
else is computation.
Yeah, and you don't know which one it is. Probably it just, I would guess that it probably just has like a FHE ciphertext of that block, and you just don't know which one it is. Because of semantic security of the FHE.
Um,
Do you think it's possible to remove the IO in the construction?
I think we should. Are we still recording?
Yeah, I think we're still recording, right?
Okay. Well, now we just
Um,
new idea.
No problem, I can stop recording.